Aaron, please take it away.
Great. So I've been working the last few years on XGC, making it ready for Aurora and Frontier. And so we'll get started. So XGC is a tokamak plasma physics code that specializes in edge physics and in realistic geometry. It's gyrokinetic, which means that a velocity dimension can be reduced to simplify some things. It's a particle and cell code with an unstructured 2D grid on each poloidal plane. And then in the toroidal direction, it's structured. So you have the tokamak divided up into a series of planes. And the domain decomposition works accordingly, where it's toroidally sliced, and then each MPI rank handles a subset of the grid, typically in these sort of ring formations. So rank 0 gets this innermost section, and then the next rank gets another ring. And the basic algorithm is that there's particles moving around the domain that scatter their charge onto the grid, and then using the charge information, you get the electric field, and then that electric field is used to push the particles to their next location. The electrons move a lot faster, and so they get subcycled 6 to 60 times per step. And then once the particles are in their new position, they have to be migrated to their new MPI rank. And after that, there's additional physics like collisions, source terms, and then diagnostics. So XGC is participating in ECP as part of the whole device model program, or ECP-WDM project. And the idea is to couple XGC with a core code, which we can couple with Gene or Gem in order to do the whole device, to model the entire device with the most efficiency. And the vast majority of the computation is spent in XGC, so its optimization is the most critical. Some challenges working with XGC is that there are a wide variety of physics features and modes that need to be supported. So you can work in delta F mode, where you're just dealing with a perturbation from the Maxwellian distribution of the plasma, or without that assumption, a full F mode. You can work with electrostatic or electromagnetic. You can run an axisymmetric case. You can run with impurities, neutrals, and then with all the different couplings to different codes. And these different modes of operation can have different performance bottlenecks. Additionally, the physics is always in a state of development. There's some changes that are just easy modular features like new sources, but then there are also structural changes that we're in the process of developing at the same time, like enabling stellarator physics, enabling 6D physics, and then different algorithms, multi-rate time stepping, time telescoping, implicit time stepping. So having a code base that can operate at exascale while also enabling all of these different types of physics is a big challenge. Another challenge is that we're trying to run on a lot of different architectures using the same code base. And so some target machines, Cori is going away, but we're still hoping to run on Summit and Perlmutter, Frontier, and soon Aurora. And an interesting thing happens because these different architectures mean that sometimes trade-offs are going to be weighed differently. These trade-offs between memory, computation, and communication. So in one machine, you might benefit from having a distributed calculation and then a gather, whereas on another machine, you might benefit from having the full calculation done on each process. And that's another reason why just flop comparisons become much less meaningful, because you can say you're doing a lot of flops, but you're also just repeating the same calculation over and over again on different processes. Another trade-off would be pre-computation versus on-the-fly recalculation. And yeah, these are going to be different for the different architectures. Some data also is better off stored on device memory if available, because that's where you're doing the computation. But in some cases, there might not be enough device memory, and so you need to be able to transfer back and forth between host and device. And so an example of that for us is particle memory management, whether we let the particles reside in host memory or device memory. And again, this will be different. The optimal solution will be different depending on the different architectures, because it depends on the available memory as well as the communication speeds. So we maintain two algorithms where we can leave particles in host memory, and then for each kernel that needs to be run, we send the memory to the device and then return it, and then send, say, the next particle species will go up and do its computations and be returned to the host memory. Or alternatively, we can leave the particles on GPU. You don't have to spend time on communication, but the number of particles per species gets limited by the GPU memory. So to prepare for Exascale, we opted to use Cocos, which everyone has probably heard of, but it's a portability abstraction layer. And we use that to map onto OpenMP, CUDA, HIP, and SYCL. And when we started off in 2019 with ECP, XGC was a Fortran code with 3 different versions. There was one that used OpenACC for collisions, a major kernel, and then CUDA Fortran for electron push, another major kernel. We had another version that was the vectorized CPU version, and then a reference version. And in 2019, we started working with the ECP COPA team to use Cocos in a very limited way, where we were still doing everything in Fortran, but using Fortran interfaces with C++ and wrappers and macros to use Cocos. And in the end, this was very tedious and inflexible and potentially not portable. So we eventually decided to just convert everything to C++, besides some non-critical legacy components. In general, we've taken the following approaches. We are working on portability with Cocos and with Cabana. Cabana is the ECP COPA developed library for particle operations that uses Cocos. We have a major focus on encapsulation and modularity, and on templating. So really trying to reduce the code base so that it's much easier to experiment and to swap out different options. And another thing that we started doing more of is standalone kernels. So most major code components can be run independently, and importantly, they all still use the same code base. So there's no free-floating copies going around of outdated code. There's no extra maintenance required for the kernels, and any improvements made using those kernels immediately benefits the full code. Additionally, we've started doing a lot more CI, unit tests, regression tests, and physics tests. What will a bigger machine do for XGC? Will the code be running just faster? Yeah, so we are going to be doing new physics that we can't do on smaller machines. That's true. Yeah, we can do bigger problem sizes and run faster. Just to answer a question in the chat. So on Frontier, with the ECP-WDM app, we were able to achieve our required FOM. The requirement was a 50x performance improvement, and we obtained a 301x enhancement on Frontier compared with Titan, running at 6,144 nodes coupled with the gem code. So that was an early success on Frontier. Coupling the two codes on Frontier raised some challenges, and we were experimenting with different I/O strategies using FS software developed for code coupling. So we had the file-based option, which we ended up using for simplicity for that run that I showed. But we also had memory-based options using MPI, RDMA, or TCP. And some of these worked, some of these didn't, and still need to be worked on and debugged. But I think the implication for Aurora is that maintaining these multiple methods for coupling is going to be helpful, because if some of them don't work, then we're going to have backup options. So that was very helpful for getting things running quickly on Frontier. Also on Frontier, we encountered a number of issues like file system problems, hangs, network and MPI crashes or hangs, and node failures. And I don't think there's that much to say about that, except we're expecting the same thing on Aurora, and we just need to be prepared for it. So we expect intermittent failures beyond our control. And that means that we need to be ready to rerun the same simulations over and over again, even if that is the definition of insanity, because the results do end up being different, because they sometimes they crash and sometimes they succeed. Another implication of that is that we need to work on optimizing our initialization, because the initialization for XGC is about the same as maybe 10 or 20 time steps. And that's amortized when you're running a simulation of 1,000 time steps. But when you're just doing this sort of troubleshooting and testing, then that ends up being way too much time to wait. So getting that all optimized is important too. So here are results. Everything from here on out is just XGC alone, running here on Frontier. So our performance enhancement from our initial summit runs to our initial Frontier runs was about 8.5x. That can be subdivided to an improvement just from optimizations, offloading. So on Summit currently, we already got a 2.2x improvement. And then moving from Summit to Frontier was a 3.9x improvement, which is compared to theoretically a 9x increase in flops. So the figure is compute nodes on the x-axis and our FOM, which is basically particle steps per time. And you can see that Frontier does a lot better. Another notable timing here is that the CPU-only MPI is actually much slower. So we got a big benefit from using GPU-aware MPI. And the reason for that is that on Frontier, the NICs are connected directly via the GPU. So if you have your data on the device memory and you're doing your calculations there, and then you want to share the result with other nodes, then you just send that directly through the NIC, the network. Whereas with CPU-only MPI, there's some extra steps, because first we need to allocate host memory, and then we need to send the results from the device to the host, and then we do the actual MPI communication, and then the same in the other direction. So the implications for Aurora there are, we think, and I wasn't sure if I was permitted to share a similar diagram for Aurora yet, but the idea is that we expect GPU-aware MPI is going to be worth using. It might not be as dramatic of a difference, but it's definitely going to be beneficial. I think the answer is no to those questions. So another topic is strong scaling, where we have the same simulation size, and we're running that simulation on different resources. And so what we find on XGC is that fewer compute nodes means less communication, and that results in more efficient resource usage. So this figure, x-axis is number of MPI ranks, and then this is basically performance, where the higher the better. And I've normalized it such that the horizontal lines are perfect strong scaling. And so you can see that we definitely don't have perfect strong scaling, And what that means is that it's always going to be beneficial for us to pack the same simulation into as few nodes as possible. And that's obviously restricted just by the amount of memory that is available. But that's a goal for Aurora, is to pack the simulation into fewer nodes to get the best performance. So a big question, since we are currently in the stage of Sunspot, where we're trying to infer things about Aurora, is, did Frontier behave the way that we would have expected based on Crusher? So at similar scales, the performance was very similar too. So that was, a good match. And another benefit of using Crusher was that we found this bug in GPU-aware MPI, and we're able to also find a workaround. And so that was really useful, because we wouldn't want to be trying to deal with full-scale Frontier while also trying to deal with this bug. So in that sense, the test bed was very helpful. But we did encounter unexpected challenges at larger scales, above 2,000 nodes. And the big issue for us is that although theoretically we had around 64 gigabytes per MPI process to work with in GPU memory, we actually in practice had a lot less than that. And part of that is because the GPU-aware MPI just requires some memory. And then another issue seems to be that there's an apparent memory leak, a bug that we've reported and they're working on, where memory getting used probably by those MPI operations is not being relinquished properly. And so this actually prevented us from packing larger simulation sizes into fewer ranks. So we weren't able to get that efficiency from packing. So for Aurora, the plan is to leave a generous memory margin, at least for our initial simulations, and then also to maintain the less performant but less demanding options like the CPU-only MPI and having CPU-resident particles, just maintaining those options in case we don't have as much memory on the GPU for whatever reason as we expected. So on Frontier, we have this weak scaling figure. So this is comparing with Summit. And the way that we weak scale is by increasing the number of toroidal planes. And you can see that we get this performance improvement from Summit to Frontier, as mentioned. And then we also get pretty good weak scaling here. Some new challenges arose due to this new higher toroidal resolution. This is a problem size that we've never run at. The particle push normally scales perfectly, but because of the higher toroidal resolution, I suspect that the issue is that we have worse memory access patterns because we don't actually sort the particles in terms of in the toroidal direction. So we might need to start doing that in order to have better scaling there. And another issue is that our plane gather routine. And that's always going to scale poorly because basically we gather the entire electric field of the whole domain onto each MPI rank. And so if you have twice as many planes, then you spend twice as much time because you have to gather twice as much data. And this is really starting to impact the time to solution. So we actually introduced a new algorithm that I'll talk about on the next slide. But generally speaking, another implication for Aurora is that there's going to be new trade-offs that might become worthwhile at scale. And that one thing I wish I had done is having these standalone component kernels that I discussed earlier, that they should be designed to imitate larger scales. Yeah, so this plane gather algorithm, basically, instead of getting the electric field from every plane, the original algorithm was that you have each plane and it computes its local electric field and then sends the results to all the other planes. And the new algorithm is that you just send the electric potential, which is a lot less data, and then do that calculation repeatedly for all of the planes. And this new algorithm turns out to be 2.7x faster on 4,000 frontier nodes. It's 6 times less communication, even though it's, if you have 128 planes, then that's 128 times more computation, but it still is better because you have that reduced communication. Yeah, so Mark is asking, so for the individual kernels that should have been designed to imitate larger scales. So what I meant was, yeah, so the push kernel that I had been testing with was not, I was not running that with 256 planes, basically. So so instead of running, I was basically running, like the kernels were designed to run smaller simulations because the kernel is on a single MPI rank, and so it's a small simulation, whereas I should have been designing these kernels to act as if they were part of a larger simulation. So this is my last. I'm going to skip over this slide, but basically there's a lot more in terms of trade-offs to be done along that same theme, including doing a secondary domain decomposition, which I think is a real interesting algorithm. But for Sunspot, just some quick status updates and comparisons. So, so these figures are weak scaling, and bigger is better here. So on a single GPU, Sunspot is outperforming Polaris and Frontier. And when we weak scale to look at the full node, then it's also doing really well, although it's kind of cheating because this is using 6 GPUs and this is only 4. So, but it's a node comparison. We've actually been encountering a bug on Sunspot that has been making it difficult to get really good progress on Sunspot. There's also been very slow link times, and that's really something I'd like to see addressed, but it takes sometimes 10 minutes to link a new executable, and that makes debugging really difficult. So to summarize, for optimized Exascale, it turns out XGC, of course, we needed to offload all of our kernels and get the computations fast, but we also needed to look at different algorithms and maintain different algorithms for flexibility on different machines. So I'm looking forward to getting on Aurora and doing science. Thanks.
Thank you, Aaron. I know you have responded to all the questions over the chat, but are there any more questions to ask Aaron?
Yeah, I had a question. So you're comparing one MI250X, one GCD, or the whole device to Aurora?
Yeah, so this, yeah, I think, so these figures are full.
It's the whole device, yeah.
Yeah, the full PVC versus a full MI250X.
Both GCDs.
Both GCDs. Okay, thank you.
Thank you. I suggest if you have more questions, you can maybe use them as in the chat, and I think Aaron can stay a little bit longer and respond to those questions.
Sure.
Thank you again. Steve, are you ready to share your screen?
Yep. Okay. Okay, how's that?
It looks great. Thank you. So Steve will talk about HACC. Please go ahead.
Yeah, so I think yeah, Aaron and I share probably very similar concerns. So you might hear some overlap with but different approaches in addressing them. So I want to talk about preparing HACC for Aurora. My name's Esteban Rangel. People call me Steve. I'm a computer scientist in the computational sciences division. So I'm just going to talk a little bit very quickly about sort of the broader picture of preparing HACC for Exascale, and then the development work that we've done supporting multiple programming models, the migration from CUDA to SYCL, optimizations for Intel's GPUs, and then I'll share some performance results and a nice visualization at the end. So in the broader scheme, in the broader picture of preparing for Exascale, HACC has had an ECP project that's called Exascale. In that project, we've run on Perlmutter and Summit, the CUDA version of our code. We've run on Frontier and on Crusher, that's the HIP version, and on Sunspot and all the JLSE systems running SYCL. We've also had an Aurora ESP project that's extreme scale cosmological hydrodynamics. So we've worked very closely with the LCF and Intel through the COE. And we've been involved really since the very early stages of Aurora through hackathons and just an ongoing collaboration that we have with Intel. We really began work with a lot of the early SDK before SYCL was really supported with OpenCL version of gravity-only HACC that we had previously run on NVIDIA's architectures. And then we've worked pretty hard on porting CUDA to SYCL and optimizing performance for the Intel's GPU architectures. And like I said, we've run on all the JLSE pre-Aurora systems. That was like Iris, DGX, Arcticus, and Florentia. So I like to show this picture because it kind of, people who are unfamiliar with the code base, kind of gives a very big picture of how HACC works on a single slide. And this is kind of the perspective of the time stepper. So HACC implements a leapfrog integrator to solve all of the simulation, and this runs in some number of steps and large time steps. So let me grab a laser pointer. So the full simulation, this is what you're seeing on the screen is a full step of the simulation. And for the hydrodynamic simulations, we run approximately 625 time steps. Now, each full step executes some number of subcycles or substeps, and the gravity component of that is some fixed number, usually about 4, and then the hydro steps are nested even within those, and those are adaptive. So a picture that's closer to the way that the code actually executes is that within each subcycle, there's basically a setup, an execution, and a teardown phase. So in the setup phase, we're allocating memory on the device. We're doing hosted device mem copies. We're creating streams, and then we execute some series of kernels, one after another sequentially on the device, and then there's a teardown phase. And the setup and teardown happens at the beginning, and basically the execution phase is the subcycling. So so this is basically what happens in that inner loop. So some challenges for Aurora is we're trying to evaluate Aurora's early hardware and SDK on a complex set of kernels and quite a few 60+ kernels. Many of these are auxiliary kernels. Approximately maybe about 10 of them are very performance oriented, and they're primarily written in CUDA and under active development. And this has kind of been the story for HACC. Right? HACC has always been an early user on many systems. So the SDK and the programming model that we're using is really the vendor preferred or vendor most supported programming model. So we typically have all of those compute intensive kernels written in for the preferred programming model for the vendor in the early stages. We're trying to minimize divergence between CUDA and SYCL versions of our code. We're trying to identify configurations and implementation optimizations that are specific to the Intel GPUs and see if there's any of those implementation optimizations that are more generally applicable. So how do we go about supporting multiple programming models in HACC? Well, if you remember that first slide or that big picture slide, there's a long range component to the gravity code that is common, and that's a host side code, and this is common really for all systems. It's C++, it's threaded. It basically is doing the long range spectral solver, and it's FFT based. So our FFT is all run on the host. All of the ancillary functions, so partitioning data, the ranked data exchanges, checkpointing IO, all of that happens on the host and is common for all the systems that we run on. And then we created wrappers for the specific API calls to CUDA, HIP, and SYCL. And those are also common, and you'll see in a couple slides. So this doesn't change on most of the host side code. A couple of points. So HACC offloads large work blocks with enough concurrency to fill the GPU, and tries to do few memory transfers. So it really copy bulk amounts of data over to the GPU. And like I said, the device kernels execute serially. So we don't have a lot of sort of asynchronous kernel execution. For HIP, we found that was pretty straightforward. We actually handle that with the macro redefinitions of the APIs. So the HIP API and CUDA API is very, very similar. So you can do something straightforward like this. For SYCL, we're really using SYCL in a very CUDA-like way. Certainly SYCL is probably more capable of the way that we're using it, with the ability to use buffers and dependencies between buffers and creating asynchronous queues and all this. But so we're really using SYCL in a CUDA-like way. So because of that, there's generally a one-to-one correspondence between the CUDA and SYCL functionality that we need for the application. So our work for preparing for Aurora looks something like: we have active CUDA development. We run through SYCLomatic. So this is a migration tool I'll talk about in just a second. We have a SYCL Functor tool that is Clang based, and I'll give some more information about that. And then that is basically what turns our kernels, gives a source code to be able to plug into the main simulation code. The SYCL Functor tool has some convenience functions for just doing some source remapping, and it converts our device functions to functors. It will also replace the DPCT namespaces that come from SYCLomatic into more standard SYCL and self-salute portability. So we also have a test harness where I won't talk about this very much, but it's been a useful tool for us. And what this is we create these kind of GPU checkpoints. So we take all of the data that's on the GPU at any instance, at any point in time during the simulation's execution, and we can save these to a file. And this test harness allows us to replay individual kernels on actual live data taken from a simulation, in such a way that you don't need to build the entire simulation code. So these are drivers that can sort of bootstrap all of the information that was taken during a live execution of the simulation code and replay these individual kernels. This has been super helpful for doing code and configuration optimizations. We work pretty closely with Intel using this tool, and we've been able to explore alternative implementation algorithms and the performance impact associated with those. So this is, I won't talk about it more beyond this slide. If there's questions later, go ahead and please ask. So other than that, we of course need to write the individual API wrappers for the different implementations for CUDA, SYCL, and HIP. So here's what these common host interfaces for these API wrappers look like. So this is inside the host side code that's shared across all of the implementations. So we have basically a wrapper for invoking the GPU kernel and things for like doing GPU mem sets, mem copies. All these things have wrappers for the individual programming models. And so here what we're doing is we're invoking a kernel and basically calling a device function with all of the parameters needed by that function. So on the CUDA side, what does that implementation of that wrapper look like? It's a series of kernel wrappers. In this case, it's a template argument. We take the type of the kernel. We end up using, isolating that pointer type and calling one of these invocation wrappers. But on all of this code is responsible for launching that CUDA kernel. On the SYCL side, that same implementation is slightly different. So we can't use the function pointer, but we do have a functor implementation that also is template based with a slight macro that wraps that kernel invocation. Basically, this macro takes the function name as the first argument, puts it as the template parameter, and then that lets us call this invocation wrapper. Inside here, instead of sort of the triple chevron kernel launch of CUDA, we have our SYCL parallel for and all of the associated arguments needed to launch that kernel. So basically now through this common interface, we can launch CUDA kernels and SYCL kernels in a way that's similar to the host. So to do the actual kernel translations, we do leverage SYCLomatic. An important note, I guess, is that code organization wise, all of our CUDA kernels are in their own files, so their own translation units. And this is important because the way that we use SYCLomatic is this single file migration, so one at a time. Using SYCLomatic, we've used it for quite some time. We've made feature requests, we've found bugs, we've reported them. Here are a few examples. One thing that we did ask was when SYCLomatic was known as DPCT, we did request for it to be open source, and the team was very accommodating, and I think that was a very good move on their part. So now DPCT is now SYCLomatic, and it's really under active development. If you look at the Git repository, there's commits from like 2 weeks ago, probably. We also use one of the new features of incremental migration. So in our code and many codes, user macros often define alternate code paths. So SYCLomatic now lets you change some of these macro definitions, rerun the code, rerun the tool, and it will merge the outputs together. So making it a lot easier to handle these user-defined macros. So on the right, I have an example of the CUDA source that goes into SYCLomatic, and then what comes out of it in this single device function sort of form. And it's pretty similar in the SYCL code in the function body that's not in this example. All gets migrated to the corresponding CUDA to SYCL. And there's an addition of this ND item that gets tacked on to the argument list, which is something that doesn't exist in CUDA. So the next thing we have to do, like I mentioned, we are looking for this functor representation, so that requires a source-to-source translation. So here's an example of what comes out of SYCLomatic. And like I said, this is additionally the last argument is sort of one of these ND items, and then we'd like to turn it into something that looks in like this functor version of the same code, where we have some private data members of the class, public data members that also include the call operator And now the ND item is the one and only argument needed for the call operator. So to accomplish this, we have this tool that we created that's part of Clang Lib Tooling. And here we're using the actual the public version of Intel's DP++ compiler that actually is similar to the Clang release, supports standalone Clang-based tools via lib tooling. In this tool that we created, we use the recursive AST visitor functionality from libclang tooling, and the AST. We can parse the SYCL files, and we can recursively traverse the AST. We can find all of the functions that we want to migrate. And one thing sort of to requires a little more effort is that if we have macro definitions, you need to be a little more careful because these tools run after the preprocessor. So you need to use a source manager to get around some of these things. But it builds with pretty little effort. And I think it's a nice complement to this pipeline that we have, an important stage in this. I'll talk real quick about some performance optimizations. This isn't encompassing all of the work that we've done, but some kind of relevant work that had a big impact. So in our kernels that we're executing, these are CRK is a SPH formalism that we use inside HACC. A lot of our kernels are of the form where there are computational symmetries involved. So what that means is if we're interacting particles in two leaves, the particles, when a particle in one leaf is interacting with a particle in another leaf, the same needs to be happening at there's a symmetric calculation that's done on both sides of in both particles from both leaves. So this equation isn't the only one with these symmetries, but I think it's a good example. What this means, at least in this half-warp implementation that we have, so this is basically an implementation characteristic, is that we load up half of the warp or half of the SIMD with particles from leaf A, and then half of the warp or SIMD with particles from leaf B, and then the interactions happen between corresponding lanes. So if lane 0 is interacting with lane 4 at the same time is interacting with lane 0, and so forth. So these the way that we do this in CUDA is with CUDA shuffles, and the corresponding SYCL subgroup function is select from group. And we can also do this with the permute group by XOR. The table here is showing all of the exchange patterns that is happening with 32 lanes. Yeah, this results in on the Intel GPU performance that really isn't what we expected with or that we see with CUDA. And I mean, just the contribution of this alone was roughly about maybe 2.5 times the performance difference. So one thing we did was to then re-implement this kind of subgroup exchange with shared local memory. And here's just a very simple sort of implementation of that. But initially, when we are about to launch the kernel, the code reserves some amount of SLM data. And then what we're seeing here is basically each now the exchange happens in such a way that each item writes what it wants to exchange into SLM. Then we have a barrier, subgroup barrier, and then each item, work item, then reads the lane that it wants to read from, and then just returns the data type or the data element. And I really now going through shared memory like this basically covers all kinds of data exchange patterns at the expense, of course, of using shared local memory. But it turns out this cost is with for the particular data exchange that we have executes a lot faster than the in-register group functions like select from group and even XOR. We are aware that there is some optimizations in IGC that have fairly recently been implemented. We haven't had access to be able to test them yet, but the XOR, at least, probably in the not too distant future, we'll probably get a nice speed boost, and we'll be comparing that performance soon. We've also been experimenting with inline assembly. So far, inline assembly, this is a very optimized version of the exchange pattern that we use in HACC, implemented in inline assembly. So this isn't exactly the XOR pattern. This is I didn't have enough time to dive into all these details, but this is a similar exchange pattern that preserves the pairwise symmetry, that isn't exactly XOR, but is a kind of cyclic shift on half the SIMD width. And this is a lot closer to the SLM implementation that we have, maybe 10% slower. We're still experimenting with this, but I thought it'd be good to point out at least that these kinds of low-level features exist in case people are interested. So I'll talk about some results now. The results I'm going to mention are really using just SYCLomatic for the CUDA to SYCL kernel migration with the original half-warp algorithm, and the SLM implementation. Yeah, so almost minimal effort using SYCLomatic, assuming you wrote some wrappers, and if something like the subgroup exchanges were a bottleneck, then something like SLM will gain pretty good performance, at least as things stand now. So this is a comparison run that we set up. It's 256 cubed particles for both dark matter and baryons. It starts at Z of 200 and ends at Z of 50, which is all still pretty very early universe. It's 5 simulation steps, 4 subcycles, and if you remember from one of my first slides, this is not very many steps, what we would use in production, but it does capture sort of the characteristic computation well enough for us to understand performance. The number of hydro subcycles is fixed, so it's not adaptive. We ran these on Sunspot on one node, and we're running on one PVC for many of these comparisons, for 4 ranks per PVC, and that's just to have a fair comparison with the A100. Wall time's approximately 3 minutes. So timing breakdown. So one thing that we noticed too, that we do get quite a bit of a speed up, is to use Intel's large register file. So this is a 256 GRF. So all of these in the legend here, the ones that end with 256 are using this large register file. What that means is that we use half the number of threads on each compute core. So instead of 8 threads, we're using 4 threads. But that gives us basically double the amount of registers per thread. And we also experiment with using SIMD16 and SIMD32. So that's the leading number on the legend too. So at least in this implementation, we see that SIMD32 with the large register file gives us pretty big performance improvements. That's probably related to our register usage. We do, many of these kernels are pretty register heavy, and yeah, and so the flexibility of using the large GRF is definitely something to explore if you have register heavy code. And these big spikes are all the hydrodynamic kernels. So you could see, in at least, with the resolution of this simulation and the configuration that we have, the vast majority of time is spent in the hydro kernels. Some relative performance compared to the A100. So here what we're doing is we have GPU-FOM where higher is better, and we're comparing full MI250X and full PVCs to relative to an A100. So as you can see, we get pretty good performance, and this is in HIP. So on the code running CUDA on an A100, running HIP on AMD, and running SYCL on Intel on the Intel PVC. And using the large GRF, we've been able to get the best performance so far. And similarly, we have a weak scaling plot. So compared to Crusher and Sunspot, basically we get pretty linear, as expected, weak scaling. And HACC is really designed to weak scale, and with the problem size tailored to the individual node size. So we actually don't perform a lot of strong scaling runs. So last is I'd like to show just the verification and a visualization of a movie. This is basically a full time step version, or a full version of the simulation code running with all of the time steps that we would run in a typical production run. Of course, it's very downscaled, but this mimics exactly the kind of computation that we would do. Similar to 56 cubed dark matter and baryons, now starting at Z of 200 and V of 0. So this is the full time scale of a real simulation with the full 625 time steps for gravity subcycles and adaptive time stepping for the hydro subcycles. We ran this on Sunspot. This is a single node, but one rank per PVC tile. So again, this is how we would run in production. And this wall time is approximately 6 hours. We validated the results using the matter power spectrum to a reference run on an A100 with CUDA, and we're within our numerical tolerances. So now at least we're verifying that we get the same answer. So here's the movie. So on the left panel, you're seeing gas temperature, and on the right panel, you're seeing the velocity magnitudes. And as the simulation is progressing, you're seeing the matter clustering that happens in an embodied simulation. Now in the more dense regions, you're seeing higher temperatures as a result of the baryonic physics. And similarly, on the right side, in the clustered regions, you see higher velocities, and so these are the virial regions of the overdensities, right? The particles that are falling into these overdense areas and virializing, and that results, with the higher gas temperature. Yeah, so another way for us to sort of visually determine that the code is indeed doing what we expect it to. And this was produced on Sunspot, like I mentioned. This is our team. Many of our members, work on Frontier right now, and a handful of us spend a lot of time on Sunspot. That's the last slide I have.
Thank you, Steve. We have one question in the chat who's asking about the types of, I guess, the science or the questions that HACC is trying to answer on Aurora. So can you comment on that?
So we'll be running hydrodynamic simulations. One of the things that we'd like to do is run sort of these twin simulations, gravity only simulations, and hydrodynamic simulations. Hydrodynamic simulations can incorporate a lot of additional physics. So I showed a movie with adiabatic only physics, but we have subgrid physics for doing things like star formations and AGNs and galactic winds and cooling and a bunch of stuff related to galaxy formation. And what that helps us do is basically understand where galaxies are forming, where they're distributed. And in the twin simulation that's gravity only, we can then use some of the techniques that we have for basically populating gravity only simulations, which are much cheaper to run, and see how well those schemes are working. So that's that's one of the questions that we're trying to answer. Certainly there's many, several more, but yeah.
Thank you. So I guess the next question is, have you tried to run SYCL version of code on A100? And if yes, what was the performance in comparison to the native CUDA?
That's a very good question. So we are doing that, and the test harness that I mentioned, that I said has been very instrumental in the development work that we've been doing. It's sort of the easy way that we've been able to test some of those things. So early tests that have been done have shown actually quite good performance using the Intel compiler with the CUDA backend. So the performance that we've seen on the A100 versus what the CUDA version on the A100 has been quite comparable. Yeah, that's actually been, we've been very happy to see that. At some point in the future, it's not crazy to think that we might have one code base. Yeah, so we are exploring that, yeah. And we also are exploring running SYCL with the AMD backend on the MI250X.
Thank you. Are there any more questions?